Okay, we're going to talk about some period measures. We have been talking about cohort measures. We're going to talk about period measures now. And we're going to come back to something that I had talked about earlier, which was the crude birth rate and the crude death rate. And earlier I had set things up when we were talking about the balancing equation, where we looked at the ratio of the numbers of births to the population at a particular time in the past. And I called that a ratio. I said that later on I'd be a little more formal and explain exactly what we were using the denominator, and that time is now. So here we have the crude birth rate in the year 2020. It turns out to be in the numerator the numbers of births in the year 2020, and in the denominator, in order to make this a true rate, then we want the number of person years lived in the year 2020 so that we can get the exposure to the risk of having a child. So it's person years lived in 2020 is the denominator. The same thing happens in the crude death rate, our little d in the year 2020. We take the number of deaths that occurred in the year 2020 and we divide it by the person years lived in the year 2020. We'll remember that at this point we're still talking about crude rates which are not differentiated by age. Later on we'll talk about age-specific death rates and age-specific birth rates. But right now we're just talking about the aggregated death rate, the aggregated birth rate over the entire population. So if you do this thing, if you look in official statistics, typically what they use for the denominator of these rates is the mid-year population. That is their estimate, their best guess at the population in this area that we're looking for on July 1st of each year. So why? How do they get from the mid-year population to the person years lived? Well, let's draw a little picture, because I like drawing pictures. Here's the population. So we're going to look at the K of T. And here T is, let's say, January 1, 2020. And here is December 31, 2020. And we say we had the population there, and we had the population there on those two dates. And now, we could look at the growth rate per day, or it turns out that if the population has been growing relatively steadily, so remember the growth rate is going to turn out to be very close to the birth rate minus the death rate. So if the population is growing, then it looks like this. If the population were decreasing, then it might look like that, okay? So here is R is positive, here's R is negative, this is 1, 1, 20, and this is 31, 12, 20. And what is the number of person years lived? We saw how we could do that when we looked at the Lexis diagram. That's going to be the area under this population curve. So it's going to be this entire area under here. So we had the number of people, that's going to be the population, and it's a year wide. So if we count all of that for each day, and we counted the area underneath that curve, that will be the person years lived. That'll be the person years lived in 2020. How can we approximate that? Well, if this were close to linear, we could approximate that by a rectangle. And that rectangle looks something like this. The same thing would occur here if the population growth rate was negative and the population was decreasing. Then we could approximate the area underneath the curve over here with this red rectangle. How wide is this rectangle? This rectangle is 1 year wide. How high is it? Well, if the population was growing evenly throughout this period, it will be very, very, very close to, if this was halfway, it would be very close to the population in the middle of the year. So when we say that we use the mid-year population, we're actually taking the height of this rectangle on July 1st and we're multiplying it by its width, but the width is 1 year. So that's why we use the mid-year population for yearly rates. If we were looking at a longer period of time, like a decade, then we'd have to take the mid-period population. It's 10 years wide, so we're looking for halfway, and that might be 5 years. So we would take that 10-year period, we would find, say, that 10-year period from January 1st, 2010 to December 31st, 2009. Then we would, that's 10 years, so that we would find that the halfway point, that's 5 years, so that would be January 1st, 2006. And then we would get the population on that day, and then we would multiply by 10, because there are 10 years wide, so that'd be a 10-year period. So in that case, if we were looking at decadal rates over a whole decade, then we would take the population halfway through, not the mid-year, we would take the mid-period population. So the general rule is we use the not the mid-year, the general rule is use mid-period and multiply by the width of the interval. So that is why when we do annual rates, people look at the mid-year population. It's an estimate of the person years lived. Okay, I said earlier, let's start a new topic, that when we do period life tables, we now know how to calculate period years lived, person years lived. That's the vertical strip. But we had a problem, and our problem was that in order to create the life table, we need to have an entire column. It doesn't quite make sense to look at survivorship because in the period, people are born from different cohorts. So there's no standard to compare against. So typically what we do is we base the period life table on the mortality rates, the NMXs. We can calculate the NMXs by looking at the numbers of deaths for a particular age group divided by the population at risk, and that would be something very close to the mid-year population. So if we wanted something like 5M20, that's the mortality rate between ages 20 and 24. In the year 2020, we would take the number of deaths people aged 20 to 24. We would divide that by the person years lived in the year 2020. The number of person years lived in the year 2020 by those who are 20 to 24. And that is going to be approximately close to the mid-year population of the 20 to 24-year-olds. Once we have that, once we have all of the NMXs, then we want to convert those to NQXs. Those are the probabilities of dying between ages 20 to 24. And from there, we're going to convert that to the NPXs, which are not the probabilities of dying, but the probabilities of surviving. And once we have the probabilities of surviving, we can use that to get the LXs for a radix of 1. So we can use the NPXs and get the LXs, assuming a radix equal to 1. And once we have that, then we can proceed just like we did for the cohort life table. As I said before, if you have one entire column of the life table, then you can calculate all the other columns. In this case, we're going from NMX to NQX to NPX to LX, and then to the NDXs, and then to the NLXs, and then to the TXs, and then finally to the expectation of life. So that's our strategy, and now you can see we know how to get from the NQXs to the NPXs. We know how to get from the NPXs to the LXs. We know how to get from the LXs to the DXs and then to the NLXs. One thing we haven't covered is how do you get from the NMXs to the NQXs. Now I'm going to tell you two ways to do it. One way is algebraic. And there's a lot of manipulation. You can also do it geometrically. You can draw a picture like I have before and look at triangles and rectangles and trapezoids. And it turns out that in order to do this conversion, you can do it geometrically. You can do it algebraically. What we want to do is describe NQX as a function of the things that we know, which are basically the NMXs. We can do it algebraically. We can do it geometrically. And there's actually another way that we can talk about it, and that would be using calculus. So there are three ways. I'm actually not going to talk about the geometric way, but I'll tell you that you can do it if you draw the trapezoids and the rectangles as I've shown you before. The algebraic way, we've said this before, that it turns out that the NMX, N times NMX, NMX is very close to NQX. That's going to be the probability. How close is it? Let me tell you what the actual algebraic calculation is, the conversion. And there is I'll write it down. It is actually N times NMX divided by 1 plus N minus NAX times NMX. And it turns out that this thing is typically quite small. The only time when it's not is when NAX, remember that's the number of person years lived by those who died, that NAX is typically n over 2, so that term over there looks like n times nmx over 2, 1/2 of n times nmx. So nmx, our mortality rates, are typically relatively small. So that's 1 plus a small number. So that means that the correction over here in the denominator is actually relatively small. There's another way to do this conversion from nmx to nqx, and that goes back to, I guess I put it on a different page. You may recall when we talked about the hazard rate, I came up with this complicated thing that looked like npx equals e to the minus the integral from 0 to x of mu of y dy. No, I think that I shouldn't have it quite like that. I think I should say that is from age 0 up to age x. If we wanted just npx, that would be from e to minus from x to x plus n y. Yeah, that's better. What we can see then is that we're looking at the sum of all of these instantaneous hazard rates. If we're looking at the average hazard over this, if we assume that the hazard is constant, then mu of y dy over any interval looks like it's constant. And so this thing is going to be very close to e to the minus n times nmx. So that is actually the second way that we're going to use this. It's going to turn out that this is one way to do this conversion from nmx to get the nqx. This thing is equal to nqx. And if this thing over here is equal to this, then it must be the case that 1 minus npx equals 1 minus e to the minus n times nmx. Very close to that. So that's going to be our second way to convert the mortality rates into a mortality probability. Then once we have those mortality probabilities, then we can go in through this sequence. Now we're over here, then we can get the NPXs, the LXs, and so on. Let me talk about a particular mortality model, and we're going to talk about Gompertz mortality model. Gompertz was a mathematician, worked in England. He had to, I think he actually had to move to either Belgium or the Netherlands in 1825 or 1828, right around there, the same time that Verhulst was working on the logistic model nearby. Gompertz, Benjamin Gompertz, was working on his mortality model. So Gompertz, let's do this backwards. Let's say, if we were to, I think I drew last time some typical shapes of the life table functions. I drew a shape of what Lx looks like, what E sub x look like, what the d's look like. And then I drew a picture of what the mortality rates or the hazard rates look like. And I think that I said that the nmx's or the mu x's, that's an m. This is the mortality rate or the hazard rate by age. It's relatively high in the first year of life. It's low for a long period of time. Once you get past childhood, perinatal causes of death, it's low for a long period of time once we get past childhood diseases up to age 5 or so. And then starting in maybe the late teens, it starts to rise, and then it rises and it rises, and then it goes up like this. So this is what mortality looks like by age. So this is age over here, age X, and it looks like this. So it turns out that you can split this up into basically 3 parts. You can look at a child mortality model. Then there's a long period of time when it looks kind of flat. And then there's an older age at which the mortality rates or the hazard rates increase quickly. And so these are the child and infant group. This is sort of the adolescent group. And then over here, they call that the senescent group for people who are getting older. And Gompertz noticed that once you get past age, let's say 35-ish or 40, so from 35-ish to 40, in that range, let's make that a little bit clearer, somewhere in this range of 35 to 40, it starts to increase, and it starts to increase quickly. And Gompertz's observation was that over this period, after age 35 or 40, this thing looks nearly exponential. The mortality rate or the hazard rate increases nearly exponentially after age 35 or 40. So, being a good mathematician, Gompertz said, rather than plot nmx or mux, let's plot the log of the nmx or the log of the mux against time. And sure enough, after age 35-ish or 40, the mortality rate looked flat. It looked linear. So it's almost linear. And this is true today. This is true almost up to maybe age 85 or 90-ish. So between this 35-ish and 40 to maybe 85 and 90, the log of the nmx is almost linear. Between ages, somewhere in the age range of 35 to 40 and 85 to 90, log nmx looks almost linear. So, if that's the case, then what we're saying is that the hazard by age looks like alpha e to the beta x. And this is the Gompertz mortality model. And that's so important, I'm going to draw a box around it. This is the Gompertz mortality model. It's pretty simple. And if this were true, then the log of mu of x equals log alpha plus beta times x. So this is the other way that we describe Gompertz mortality. It is linear in the log of the hazard or the log of the mortality rate. This thing is going to look like intercept. Log alpha is going to look like an intercept. Beta is going to look like a slope on age. You can go to, if we'd had more time, I would have had you go to the human mortality database. At hmd.org, or alternatively mortality.org, and you can download a bunch of life tables for different countries for different years. So if you did this, you could download many different life tables for different countries. In different years. You can also find both period and cohort life tables, so you can compare them and you can see what the expectation of, you could track how expectation of life changed over time. But in this case, I am going to look at an example. My example is Swedish females from the 1910 birth cohort. And if you suppose I told you that for Swedish females in the 1910 birth cohort, alpha was 0.00013, and suppose I told you that beta was 0.087. Then you could calculate, using this, you could calculate what the hazard rate, what the mortality rate at age 85 would be. We know it would be it'd be, let's see, what did I say it was? 0.00013 e to the 0.087 times 85. And if I did that properly, you should check, then that was 0.1194. So that's roughly 12%. So that's roughly 1/8. So if you were an 85-year-old Swedish woman, your chances of dying this next year, your mortality rate in this next year is roughly 12%. That's 1/8. So you can do that for other years. You can download a live table from HMD, from the Human Mortality Database, and then take the log of that mortality rate and then do a regression on it over X, and then you can calculate what log alpha and beta are.